Okay, this is question number 9 of the Nuclear Physics homework booklet, and in question number 9 we're starting off by simply being asked to state which of these three types of radiation produces the greatest number of ion pairs per millimetre. What it's really asking us is which one of these three is the most ionising. We know, because we've learnt it, and we've done our revision, that the most ionising of alpha, beta and gamma is alpha radiation. For part 2, we're asked again which of these three types of radiation would be used to test for cracks in metal pipes. Well, if we're testing for cracks, then what we basically want to do is we want the gamma radiation to be affected by the metal. Well, so we want radiation to be affected by the metal, but not to be completely and utterly absorbed by it. If we're looking at metal pipes, both alpha and beta would be completely absorbed by any thickness of metal whatsoever, and so the only one we could really work with is gamma. So you get 1 mark for alpha radiation for the first part, and 1 mark for alpha radiation for the second part. We're then told that specific radioisotope sources are chosen for tracing the passage of certain substances through the human body. Radioisotopes basically just means it's an isotope, so it's an element or an isotope of an element which emits radiation, basically. So what's going to happen is some patient somewhere is going to take a liquid radioisotope, for example, drink it, and then the radiation is going to get out of this person, but using a detector they can see where the liquid is going, basically. So first of all, we're asked why a gamma radiation source is used and not alpha and beta. Well, as we've just said, radiation needs to actually get out from the inside of you to the outside of you, so you can use the detector. Gamma radiation can very easily pass through the body, and so that's why you would use gamma radiation. For part 2, we're then asked to consider, again, it's exactly the same process. So a person is swallowing this stuff, so that people can see, the doctors can see where it goes. So in terms of the actual half-life, then what we're really asked is why it shouldn't have, why this source of radiation should not have a very short half-life, whilst the doctors are basically watching where it goes through the body. Now, if it did have a very short half-life, what would happen is the activity would become too low during the measurements to distinguish from background radiation. And if that happens, then obviously the doctors can't see what they're looking for. So that's why it shouldn't have a very short half-life. In terms of why it shouldn't have a very long half-life, well, if it did have a long half-life, then it would have a high activity for a long time. So therefore the source would irradiate the person for a long time, and therefore it could cause damage. The word long time needs to be in your answer if you're actually going to get the mark for that particular part of the question. In terms of marking points, you basically got 1 mark for each of the 3 of those things. In part C, we're then given a lot more information about how this actually works. So what we've got is we've got a detector. So we've got a detector of radiation, and it's placed at 0.2 meters from a sealed gamma ray source. And the detector receives a mean count rate of 2,550 counts every minute, as it's shown in this diagram over here. And then we're told that the mean background rate is measured, and it's 50 counts per minute. So we've got this experimental setup. What we're then asked is to calculate the least distance between the source and the detector if the count rate's not going to go up and go more than 6,000 counts per minute. So because this is gamma radiation, it follows the inverse square law. So if we took this detector and moved it closer, the count rate would go up. And we're going to move it close enough so that the count rate in total doesn't go up above 6,000 counts every minute. Now, because we have been told that this is the background radiation, we need to look at actually the information we've got. So at no point in the question does it use the words corrected count rate. The corrected count rate is the count rate once you've taken off the background radiation. So what we need to basically assume is that this number and this number down here, the 6,000, are going to be the total count rates that include the background radiation. So but if we're going to think about the inverse square law, that works for the corrected count rate. So what we need to do is work out the corrected count rates first before we can then apply our inverse square law equations to it. So the corrected count rate that we're starting off with, we've got 2,550 counts altogether. we've got 50 counts per minute that comes from background radiation, so that therefore on average we're getting 2,500 counts per minute just from the gamma source. We're then going to move this closer, and in total every minute we want 6,000 counts per minute. But 50 of those on average are going to be background radiation. So actually we don't want 6,000, we want 5,950 counts coming from the gamma source. So therefore that's our second corrected count rate. We can then apply our inverse square law equation. So that's our equation for the inverse square law when this detector is at the first point. We're then going to move it closer. The same equation holds, but obviously the count rate or the intensity and the distance have changed, which is why they've now got a 2 on them, but the k stayed the same. If we rearrange this, then the k is equal to I1 x1 squared, and k is equal to I2 x2 squared. The k's are equal to each other, so that's where this comes from. Where we want the second distance. So if we rearrange this equation for the second distance, well, the second distance squared is equal to the count rate it started with, multiplied by the first distance squared, divided by the count rate that we actually want. So we just put our numbers in. So this is the starting count rate, corrected count rate of 2,500. The distance was 0.2 meters, and so we square it. The corrected count rate that we want is 5,950, which gives us 0.0168, etc. But that's the distance squared. We then square root it, which gives us a distance of 0.13 meters. So if we move this to 0.13 meters on average, we're going to get a count rate of about 6,000 per minute. So that was question number 9 of the nuclear physics homework booklet.